Let's look at this example problem where we apply Newton's universal gravitation equations to determine the acceleration and the weight of an object on an unknown planet orbiting a star in the Andromeda galaxy. We've got the equations and givens for this unit, some of which we'll use here in this problem, others we may use in future problems. But let's start this problem by setting up what we know in the problem. So here they tell you something about the planet. They tell you the mass of the planet and they tell you the radius of the planet, right? And we're dealing with gravity, so we're dealing with large masses causing gravitational fields, right? So let's write the values we have. We know the mass of this unknown planet, they tell you, is 2.85 times 10 to the 24 kilograms. That's the mass of the planet. We also know the radius of that planet, and the radius of that planet is 6.25 times 10 to the 6 meters. We know big G up here. I won't write that down. That's given to you in the problem, right? And when we're talking about an acceleration, we're talking about the acceleration due to gravity, right? And that's what we're trying to find here for part A. And we have an equation for the acceleration due to gravity of an object. And that equation, I also like to consider it as the field strength of gravity. AG is big G, the gravitational constant, times the mass of the object creating the field, divided by the distance to the center of that object, which that distance would be the radius, right? This is the radius of that object if we're on the surface of that object. Now, if we're out orbiting away from that object, we'd have to consider the full distance to the center, right? So since we're on the surface, right, near the surface, we can assume that the distance in this case is the radius. So really we have a plug and chug. We can take that AG, which is what we want. We're going to plug G, 6.673 times 10 to the negative 11. That's our gravitational constant, G. The mass of our planet that's causing the gravitational field is 2.85 times 10 to the 24 kilograms. And we're going to divide that by the distance to the center of that object, which in this case would be the radius, 6.25 times 10 to the 6. And don't forget that that is always squared in this equation. All right, so really we can now pull out our calculator, and one of the challenges in this unit is dealing with these really large numbers. All right, so I'm going to show you a couple of little tricks here we can do. The first trick that I would suggest is let's put 6.673 second e to the negative 11. Again, when you're doing scientific notation, you use that EE feature, that double E. It shows up as one little capital E. That is the gravitational constant. We're going to be using that a lot in this unit. So I'm actually going to store this value, STO. If I hit STO, I get the little arrow. And we're going to store this as alpha G. Right? So now, every time I type in alpha G, the green keys are with the alpha, I get this value. Right? So now I can take alpha G, and I can multiply that times the mass, 2.85, second double E to the 24, that's the mass of the planet. And I'm going to divide that by the radius squared, 6.25 second E to the 6th, and I'm going to square that. Now, some of you guys might say, well, be careful, we've got to deal with parentheses in the denominator. Well, not when we use the double E feature, because it assumes I wrote out all those zeros. All right, so I can actually write it like this. I get an acceleration of 4.87 AG. The acceleration due to gravity is 4.87. And what would that acceleration be? Well, field strength is newtons per kilogram of mass brought in, but we also know that that is the same as meters per second squared, which is really probably the unit that would make sense here. And does it pass the smell test? Well, on Earth, it would be 9.8 meters per second squared. So 4.87 seems reasonable. Those units, either one of those units would work. And so that gets us our answer for part A. And now let's look at part B. Well, we now have an object that's on that surface, right? How much would it weigh? Well, we can go back to our last unit with dynamics, and we know that the force of gravity is just equal to the mass of the object times the field it is in, the acceleration due to gravity, right? So we can simply say, well, this object that we're determining, this is a 30 kilogram object, and we now know the field strength at the surface of this planet to be 4.87 meters per second squared. And so if I take my answer from before and simply multiply it by 30, I now have the weight of that object, which is 146 newtons. Now, the other way to look at this would be the force of gravity between the two objects. And this is where that second equation, this Fg equals gm1 m2 over d squared is. Well, if we consider the force of gravity not as F equals ma, but as Newton's law of universal gravitation, where he says that Fg is big G, the mass of one object, the mass of another, and the distance between them squared, well, our equation becomes big G, the mass of the first object that's on the planet, the mass of the planet itself, 2.85 times 10 to the 24, divided by the radius, or the distance between the objects, which is effectively the radius of the planet itself. And we would square that. Now, if you notice, a lot of this equation is the same as above, right? Everything in here, if you just take this part of the equation, that is the same as above, right? And then we would just take that mass and multiply it in. So we would find that if we plugged in those values into our calculator, you would also get 146 newtons, right? So you're going to see problems here where you have two objects interacting. They both have mass, and therefore they have gravitational fields around them, and they apply forces to other masses, like those another mass in their field, right? And so if we know those two masses, we can find the force between them, and effectively can find the weight of one object on that other object, right? So it's a good example problem introducing you to these two different equations we're going to use quite frequently in this unit. There'll be some algebra involved here and some big numbers, but this is a good introduction with this one here.